Okay, so let us talk briefly about perfectly elastic 1D collisions. I wanted to give you guys sort of a hint about how to do these things. So, a perfectly elastic collision, we know that we have kinetic energy is conserved and momentum is conserved. And in a 1D collision, we can treat the velocities as scalars. So here we have u1 and u2 as our initial velocities of these masses. And they're both defined so that they're going, positive going to the right. So, anyway, I'm still getting used to this program. So, kinetic energy. What I want to do is I want to say, instead of saying that we have, like usually when we do a conservation law, we say kinetic energy initial equals kinetic energy final, for example, if kinetic energy is conserved. What I want to do here is change it slightly and say, instead of saying kinetic energy initial equals kinetic energy final, I want to say 1/2, let's see, and how will we do this? M1 times U1, no, not U, sorry. Alright, M1 times V1 squared minus U1 squared. So this is the change in kinetic energy of mass 1, okay? 1/2 M1 V1 squared would be the initial, would be the final kinetic energy, and 1/2 M1 U1 squared would be the initial. And actually, I'm just going to do that. On this side, I'm going to write the, not like that, I'm sorry. I'm going to write the change in kinetic energy of mass 2, which is going to be like this. Okay? And there we go. What we know about these is that they must be, if kinetic energy is conserved for the whole thing, they must have equal magnitudes and be opposite signs, right? If mass 1 gains kinetic energy, then mass 2 must lose kinetic energy, and vice versa. So, we've got that. Now what I want to do, actually I'm not going to do momentum right below it. What I want to do now with kinetic energy is change this a little. First of all, I'm going to factor out the 1/2, I think that's pretty obvious. Okay, and I want to factor this stuff in the middle, or this difference of two squares, and you may remember from Algebra 1 or Algebra 2 that if you have the difference of two squares, you can change that into the difference of the two things that are squared times the sum of the two things that are squared. Like that, okay? So this down here is just a the second line, what I've written so far, is just a factorization of the first line, okay? And then I'm going to have a negative negative M2 times V2 minus, minus, jeez, I can't do anything right. V2 minus U2 times V2 plus U2. Okay, so that's how the second half factors, and looks good like that. So I'm going to leave that for a moment, okay, and sort of draw a little light dashed line under that, okay. And then we're going to say for momentum, we're going to do the same thing, basically, and say here now M1 times V1 minus, there we go, V1 minus U1, that's the change of momentum of object 1, and over here on the right side I'm going to do the change of momentum of object 2. Okay, and what we know about these is the same relationship they had for kinetic energy. If object 1 gains momentum, then in order for momentum to be conserved, object 2 must lose the same amount, and vice versa, so on and so forth. So we can put things like that. And so this equation, which has a lot of blank space in it, but other than that, it's the right equation. This equation down here is the momentum situation. So now what we can do, now that we've done these two, is we look at the momentum and the, what am I doing? Okay. Well, I don't know what I'm doing now. Okay. So we look at the, there we go, eraser. Okay. We look at the momentum and kinetic energy equations. What we'll notice is this here, that I'm underlining right now, is equal to the change in momentum, right? This was part of the kinetic energy equation. Okay, what I just underlined here again. This was part of the kinetic energy equation, but that's now the same as the momentum equation. And over here, this part I underlined is now the same as the momentum equation on the right-hand side, right? So what this means is we can divide through this factored version of the kinetic energy line. So we can take this line I'm putting a star through and divide by the momentum, which is right below it, and get down to v1, come on, v1 plus u1 equals v2 plus u2. And this will hold for any perfectly elastic 1D collision. This will be true. It's easier to use this often because this just sort of gives you a straight plug-in for your four velocities, your two initial and your two final. So you probably want to use this and the conservation momentum equation. So, and I'm going to write p cons for the conservation momentum equation. Okay? And now what I will say is don't just pull this one out from memory. Don't just memorize this and pull it out on a test, because chances are pretty good your teacher will, throw a flag on you and say, you're not allowed to just pull that out of your butt. You got to show me where it comes from. So what you should do is when you use this, derive it, okay? And the derivation is very simple. We just went through it, right? We start with the kinetic energy conservation and then factor that, like I said, remember that difference of two squares thing. That's the only real trick here. Doing that, and then you divide it by the momentum conservation equation, and you get to this. You get to this thing here. That check. And do that, and even better, for any given problem you do a version that's specific to that problem. So if you know, for example, that, I don't know, that say one of the objects is stationary initially, like u2, for example, if you know that u2 equals 0, then do a version of the derivation that includes, it includes that fact in it. So what I want to do is say, let's see, tell you what, I'm going to pose a problem for you here, and then do it, and that'll be the next one. I'll show you an example of how I would use this. All right.